So welcome. Today's live webinar is a featured speaker webinar where we will have a talk from Geoff Beale with Pitot Associates. He will be talking about operational water management for open pit slope stability. And then following Geoff's talk, we will have a panel discussion with our wonderful panel here today, and I'll introduce them in just a moment. So this webinar is developed by the Geotechnical Center of Excellence within the School of Mining Engineering and Mineral Resources. We are an industry-funded and member-led center, and we are committed to bridging gaps within and between academia, industry, and fields of study through a collaborative approach, and we focus on geotechnical research and education for the mining industry. If you'd like to know more about GCE, we have our email here, easy, gce@arizona.edu. And as I mentioned, we are member-led and industry-funded, so I wanted to take a moment to thank all of our members that you see here on the screen. So these are our GCE members, ranging from our executive members, leadership members, partnership members, and patron members. So thank you very much for your support. Without all of our members and our membership support, we could not do everything we do at the GCE, so we really appreciate you and all of your collaborative support. Today's webinar team with the GCE is myself. I am Jillian Noonan, Senior R&D Engineer with the GCE, and I'll be your moderator today. Also joining me is Cheryl Bukowski, who is our Professional Development Program Lead. Thank you, Cheryl, for being here today.
Thank you, Jill, and welcome everyone.
And also Lara Summers, who is our Program Coordinator. Hello, Lara.
Hi, everybody. Good to meet you.
And also here, just noting that if you do have questions throughout this webinar, you may also contact our GCE courses team, which is Cheryl and Lara, leading that at gcecourses@arizona.edu, or you can send them a chat in today's webinar. And now, someone who probably does not need much of an introduction, especially if you have taken any of the GCE's courses, as Geoff is a featured presenter in most of those courses, including a primary presenter in our water course, which is Water and Mine Operations and Slope Stability. But Geoff also serves as the Global Technical Advisor for Pitot Associates when he's not helping out the GCE, and is just a global leader in water management in mining operations. So we're very fortunate to have him here today doing a featured talk. Thank you so much, Geoff.
Thank you, Jill. I hope everybody enjoys the session. Should be good. Provided I don't talk too much at the beginning, it'll be good.
And then we also have a great expert panel from around the globe. We have Phil de Graaf, who is the Director of Giraffe Mining Consultants. And Phil, it's great to see you today. Thanks for joining our panel.
Thanks, Jill. Greetings, everyone. Looking forward to chatting with you today.
And Travis White, who is Principal Hydrogeologist with Goldfields. Travis, thank you so much.
Yeah, thanks very much, Jill, and hi, everyone. Apologies, struggling a bit with my voice, so I'll keep my talking to the minimum, but that's more time for Geoff. Welcome, everyone.
Sounding fine so far. Marc Ruest, who is the Director of Geotechnical Engineering with Equinox Gold. Marc, very good to see you. Thank you for joining our panel.
Hi, everyone. Thanks very much for having me. Thanks for the invitation, and good to see you, Geoff.
Likewise.
And lastly, we have Simon Mansell, who is Principal Hydrogeologist with Pitot Associates. Simon, thank you so much for joining. We're glad to have you on our panel today and appreciate your time.
Good day, Jill, and everybody else, and thank you very much for the invitation. This should be interesting.
Yes. Great. All right. So our panel will be standing by as we pass over to do his talk on operational water management for slope stability. All right, Geoff, I'll pass over to you. Thank you.
Okay, thank you, Jill. I've got a few, probably 20 slides put together just to kind of set the scene. So I'll get through them as quickly as I can. Okay, so I've got essentially 8 topics and 1 or 2 slides per topic. So we're just going to set the scene and talk about the role of water in slope stability. I think what's becoming increasingly apparent to the global industry is the role of the excavation damage zone close to the slopes. We'll talk a little bit about the structural geology model, how to characterize pore pressure, surface water, input of water into geotech analysis, talk a little bit about transient pore pressure, which again is, I think, becoming increasingly apparent that controls a lot of instability or triggers a lot of instability. And I'm going to finish off with looking at 5 key challenges that I think we have in the industry just to promote the discussion. So 2 goals for water control. One is operational, the other is slope stability. And if you look at the pictures on the right-hand side of each of these pictures, the pit is dewatered purely from the dewatering wells. The water's lowered. There's no need to depressurize that side of the pit. But if you look on the left-hand side of the pictures, there's 3 primary cases where we need depressurization. One where we have weak rocks and low permeability rocks in the slope. Second is where we have structures and water will tend to dam up behind the structures. And thirdly, if we have either flat-lying structures or lithological contacts, water can then accumulate above the contact, even though the water level, the main groundwater table, has been lowered. And those conditions can occur sometimes, even if we're above the water table. It can occur either because of rainfall or because of leakage from a river or a stream. So mine dewatering and slope depressurization are interrelated, and if you don't dewater, then it's very difficult to depressurize. So just a couple of slides on the role of water. The first one is water. Actually, if you increase the water, it reduces the resistive force. And very quickly explain the effective stress concept. If you look at a failure surface here, or more likely on an inclined plane in a pit slope, what holds this surface together, or what holds any surface together, is friction. And the friction is caused by the weight of material above the failure plane. So if there's no water and there's good friction and there's weight, the block doesn't move or the plane doesn't slide. If we add water to it, it causes the block to float, it reduces the frictional resistance, and it reduces the shear strength. So the presence of water reduces the frictional resistance and reduces the shear strength and causes the block to have more tendency to slide. So that's the fundamental concept of the effective stress concept, and it's fundamental to any geotechnical engineering study or any slope stability study. But sometimes we forget that water also creates a driving force. So if this was a mine in Indonesia, where you can see there's this big fault surface behind the slope, and what happened is the water was dewatered in front of the slope, not behind the fault, and the driving force caused this 250 meter high instability, primarily caused by the driving pressure behind this structure. This is a mine in Suriname, where it illustrates how water can get into the vertical jointing. The vertical joints can hold water on one side but not on the pit side, increases the tendency to topple. So those are examples of driving forces. So we have to consider mostly the resisting forces, the effective stress, but secondly, the driving forces. I think most of us in the industry are becoming more aware that many of the instabilities occur shallow to the slope, in the zone where the rock has been either damaged by blasting, degraded by the passage of water, or where the fractures have become dilated, particularly the slope parallel fractures, as a result of the reduction of stress as we mine the pit. So this is the excavation damage zone. It's a large pit. In a large pit, it can be a couple hundred meters more. In a smaller pit, it can be 60, 70 meters. So we have these two zones which are gradational, the blast damage zone in yellow, the excavation damage zone in brown. And what we see more and more is the water tends to be in the shallow material, the weathered material or the overburden. It goes into the slope, and its path of least resistance is down the slope. So rather than water flowing from the pit slope into the pit, we're in the situation which is common in many, many mines, where actually water flows from the slope back into the formation. And that can create recharge for the formation. It can also create these driving forces, as you see here. So I think we're becoming more and more aware of the excavation damage zone in geotechnical engineering. So this is a project in Russia that I worked on. Similar situation where we have this water. The path of least resistance isn't through the formation; it's through the jointed, fractured, higher permeability zone close to the slope. This you see here is this failure here. So you can see water from the upper part of the slope has got into a failure surface and caused the instability. Similar here, this is a project in Chile where there was an 18 bench failure, but it was only 20 meters behind the slope. And then you can see in this pit, you've got these sub-parallel joints which have opened up because they're parallel to the slope. So the excavation damage zone and dilation of fractures are important concept. The structural geology model is fundamental to geotechnical engineering, fundamental to hydrogeology. The vast majority of faults will act as flow barriers across their strike. Some of them have enhanced flow along their strike, but the vast majority create barriers across their strike. And there's 4 reasons for that. Is they offset the geological units, they soften the rock and heal the fractures adjacent to the fault plane. Often they've got presence of fault gouge, and often you get the formation of fault parallel fractures parallel to the fault. So those 4 reasons contribute to what we see in the field, that most faults, not all, but the vast majority of faults act as barriers to groundwater flow. Other important concept, as I've been saying in the past couple of slides, is that many hard rock mines, we see depressurization of the hard rock, very low drainable porosity. If there's any interconnectional fractures, this will depressurize. But the weathered zone, or the softer material, or the overburden, will very often stay saturated. I took this picture several years ago in Saudi Arabia. This is just to illustrate that. You can see the rock actually down here is depressurized. The water's running from the upper weathered zone through this fracture and into the pit. So much of the flow that we see in many hard rock mines is actually shallow water which moves down from above. And that is a challenge when it comes to predicting slope stability and carrying out hydrogeological analysis. The key problems we often get are where we have dilated fractures, slope parallel fractures that dilate. If they dilate, surface water runoff from the ramps can get in. They can get in, create driving forces. This is a good example from Arizona, where you see the instability is right at the place where the fracture, or the fault in this particular case, is parallel to the wall. So the fault has dilated, water's got in and created this zone of instability. The water's trying to push the wall out from in front of it. just an example of that, I drew this picture a couple of years ago, and it's gone all over the place. It's gone a bit viral. It's in the new slope design book, which is about to be published, but it shows exactly the same thing. Many of our slope instabilities, they're not caused by the groundwater table down here. They're caused by shallow water percolating into these what I would call dead-end fractures, reducing the effective stress on these fractures, but as important, probably creating a driving force which pushes the material in front of it. And often then you get progressive instability as one fracture dilates, the one behind it dilates, and so on, to coalesce to often give a larger unstable area. So characterization of pore pressure, one of the things I repeatedly say to operations is that we've got the grouted in vibrating wire piezometer. It's revolutionized mine geotechnical engineering. We can put as many sensors in holes as we want, and we can see vertical differences, vertical gradients, and really get to understand what's controlling the instability. So this is probably, I would say, the single most important advancement in geotechnical engineering over the last 10 or so years. What I repeatedly say to people is, yep, they're fine, but for slope engineering, we have to put them in close to the area that we think the deformation is going to occur. Many times we see them too far back behind the slope to be useful for slope engineering. So surface water is another one of my hobby horse, high horse, soapboxes, whatever you want to call it. I've been tailing surface water now. Gave a keynote at the Slope Stability Conference in South Africa more than 10 years ago now. And we see it's more and more instabilities. I'm dealing with 3 very large instabilities at the moment, which are purely triggered by surface water. A couple of examples here. Again, slope parallel structure. Water is able to run all the way down the ramp. Ponded here, you can see what happened. This is another example where the ramp was graded towards the slope instead of away from the slope. It was graded towards the crest. You can see there's a slope parallel fault here. Water came down the ramp into the fault, and the rest is kind of history. They've had to run this ramp. It's a big pit. They had to run this ramp a single pass ever since that incident. So surface water is becoming a real issue in slope engineering. So excavation damage zone, shallow instability, surface water, all interrelated. And the thing with surface water, you can build diversions, but if you can't maintain them, the diversion actually will concentrate the water. If you can't maintain it, this is a pit crest diversion. See what happened? You can see how they remediated this. This is another pit crest diversion. See what happened? The diversion failed. They put a pipe in there. The pipe failed. So if you can't build it, if you can't maintain it, don't build it. And again, maintenance is a very difficult thing to control around an operating mine. So input of water into geotech analysis, we all tend to jump on numerical models, but there's 5 approaches, and we could probably talk a little bit more about this in the session that follows. We can use RU, which is just the proportion of proportion of upward force compared to the downward force. We can use simple phreatic surfaces and vary those. We can use HU, which is this example here, which is the departure of the piezometric surface from the hydrostatic condition. So if we're 10 meters below the water table and the water pressure is 5 meters on a piezometer, then the HU is 0.5. We can use a pore pressure field, and of course we can do 3D or 2D analytical or numerical models, or we can input, if we think we've got driving forces, we can input the water into the discrete features. Many, many models that we see are becoming extremely unfocused on the stability that we have to deal with. This is a good example. You can see where the stability is. When I walked onto this site first, they said water's not an issue. The water was running down and causing this to fail. They built a groundwater model. They put this phreatic surface into the groundwater, into the geotechnical model. They put a groundwater model, phreatic surface into the geotechnical model. It was below the level of the failure. Of course, it's going to make no difference. The issue is shallow. The groundwater model is too deep. And actually, this is one of Travis's. This is a great system. This is for dewatering. But what many of the Anglo-American mines do is they just track their dewatering history in a simple spreadsheet or in a goal sim analysis and use the empirical data to forward predict the drawdown for a given pumping rate. So what you see here is the predicted drawdown from an analytical model for 3 different pumping rates. Very well focused, honors the data, easy to operate, gives reliable answers. And the final challenge that we have is, or the final topic to think about is transient pore pressure. It rains or the snow melts, the water gets into the failure surface, and it then triggers the instability. So transient infiltration, transient pore pressure is also an issue that we're increasingly becoming aware of. There's getting to be lots of data. This is a single piezometer in a multi-piezometer set. You can see this piezometer. You can see the transient response to the rainfall here. And this is a picture I've used for many years. This is a mine in Indonesia, and this is seasonal, so this is many months. The deep piezometer responds to the 4-month wet season. The shallow piezometer in the same hole responds to discrete rainfall events. So you can see just the depth of the piezometer below the slope gives us a completely different response. And in fact, these transient spikes in pore pressure were driving the failures at this particular operation. So what are the 5 challenges? So I think firstly, let's try and focus the piezometers. We've got great ability now to put in piezometers with the vibrating wire. Let's focus them on the areas where we think it's going to fail. Let's not put them miles away from the pit. Let's focus them where we think we need them. Let's understand and focus our field test results. And I've got a slide for each of these before we get into the discussion. Make sure we apply the structural geology in a intelligent way. Surface water almost goes without saying. More and more instabilities I'm seeing are triggered by surface water. And then, as we've just said, let's use the most appropriate analysis. Let's not just jump into a numerical model. So, firstly, the piezometers. This is a good cross section. We had to dewater these, so these piezometers are back here. But this is the critical failure surface. This is the most important thing for stability. So we got the piezometers focused right in the area of instability, right at the toe of this critical failure surface. So we understand the pore pressure in the most critical part of the slope. So we've got the piezometers focused where we need them. Increasingly, I'm starting to recommend horizontal piezometers purely because you can put them in close to the slope, and you can put them in with operations, and you can put geotechnical TDR cables in to look at. So we then look at both the shear and the pore pressure in the same hole. So this is going to become more and more. We're going to see this more and more as we go forward. This is a project I was working on last week where you see they've got horizontal drains, but you see they've got the horizontal piezometer as well. Horizontal piezometer put in so it crosses these slope parallel structures. Very good focused instrumentation. So that's the first thing. Let's focus the piezometers where we need them. Secondly, let's really start to understand field test results. See, many packer tests, but packer tests only tell us what's going on in the immediate vicinity of the hole. They tell us nothing about the flow in the wider formation. So one of the things that I see at many sites is the misapplication of packet tests. We can do lots of tests, we get values for numbers, but all they tell us is the local rock mass permeability. They don't tell us about structural controls, flow, only they tell us about the local rock mass permeability. So rather than do that, we're starting to put in vibrating wire piezometers and airlift, inject, or even pump holes adjacent to the piezometers. So this is an example of a piezometer with four sensors in it, where we had drilled a hole next to it, and you can see the response in each of the piezometers. So now we know how groundwater is flowing. We know empirically that if we put water in, it rises, or if we take water out, the pressure will fall. We have great empirical data. We can then calibrate our analysis for that data. This just tells us a spot permeability. This tells us the wider flow field. And two fundamental considerations for any mine hydrology. Firstly, groundwater flow seldom follows the hydraulic gradient. We see lots of contour maps with the contours and the flow lines perpendicular to the contours. Very rarely does that happen. Here's a more typical situation where we have faults here, or in this case, bedding here. The hydraulic gradient is towards the pit. The flow is essentially parallel to the pit slope. Doesn't follow the hydraulic gradient. And then this is an example for where you misapply packet tests. The flow from going from right to left is controlled by the least permeability part of the system, the fault. So unless we characterize or understand the fault, we're not going to understand groundwater flow. So we can do as many packet tests here or here as we want, but they're not going to characterize the flow because the flow is dictated by the lowest permeability part of the system. And I use the analogy, if you have a 10-inch pipe and a 2-inch valve, the only thing that controls the flow is the 2-inch valve. It doesn't matter what the diameter of the pipe is. Similar with groundwater flow. Surface water, yep, as I said, it's becoming increasingly controlled. This is a well-designed ramp, crossfall on the inside, keep the water away from the crest into the slope. You can see this is the same ramp. They had some leaky pipes on their pumping system, but the water ran down on the inside of the slopes, away from the dilated joints on the crest. Just managing the ramps like this will give an enormous benefit for many operations, even those in dry climates. And then finally, the application of models. This is a typical flow model for an open pit mine. It assumes groundwater is going to flow towards the pit walls. The reality of it is that in many hard rock mines, the water starts in the weathered or in the alluvial or in the quaternary materials, comes down the pit walls and actually goes exactly opposite direction to the model. The water goes from the overbreak zone into the formation. So exactly the opposite to what you modeled with the groundwater flow. So that is a really also a common source of error. We're trying to do theoretical models for situations where models don't apply. So I think that was it, guys. So I hope you got some insight, and I hope I didn't talk for too long. So we've got now 35 minutes of discussion time. So I will see what our learned panel think of all that.
All right. Thank you so much, Geoff. That was a really great talk. I'm going to go ahead and switch us back to the gallery view so that everyone can see our panel here. But yeah, great talk, Geoff. Thank you so much. You covered a lot of very important topics, and I'm sure we have some great basis for panel discussion, which is what we're going to move into now. All right, so I will invite our participants to go ahead and enter questions into the Q&A at this point, and you may continue entering them throughout the remainder of the webinar. But we do have some prepared questions as well to start off. So our first one here that I will bring up is one that I think, since we just heard from Geoff, maybe I will direct this first towards one of our panelists today. Travis, I'm sure you won't mind starting us off with this question. I'll read it through to give you some time to consider, and then we will open up to the rest of the panel as well for discussion. So what is one operational water management practice that mines consistently underestimate, yet delivers significant slope stability benefits, in your opinion?
Awesome. Thanks very much, Jill, and thanks, Geoff, for the presentation. Look, there's a bunch, but if I'm going to pick one, I think proactive surface water management is a big one. Geoff covered it.
You got it right. You got it right.
It's many mines actually operate in sort of semi-arid regions, and the mines that operate in near the equator generally have it down. So it's generally the sites that don't get a lot of rain or don't have to deal with a lot of surface water that have these surface water issues. And I call it rainfall amnesia. The mining engineers often forget that, yes, it only rains 3 times a year, but when it does, there's causes a lot of issues. So, and I say proactive surface water management because you're going to have to manage the water anyway, and there are controls and things you can get in place that just make your life, a hell of a lot easier. So, very simple things, on the housekeeping side, a few things, in terms of discipline, like road construction, your camber and your gullies on the high walls, on the toe of the high wall and rather than the crest, and just very, very simple things that areas in high rainfall or high rainfall areas just do, as sort of second nature. So I'd say, yeah, proactive surface water management, very relevant and one of the big ones.
I'm glad you said that, because that's exactly what I would have said. And I'm dealing with, 3 very large failures at the moment in arid or semi-arid areas, which are very clearly triggered by surface water runoff.
I could add to that there's a reluctance from many mine operations to admit that they have infrastructure which infiltrates near the pit crests, and it's a hard sell internally.
It is.
To solve that problem. Yeah.
It is. That's a really good point, Simon. It can be. It's only one of the mines that have just had a massive failure. The general manager said to me, I had no idea that surface water was so important.
I suppose also related to that infrastructure point, Simon, is not maintaining that dewatering infrastructure. So having pumping infrastructure and piping that leaks like crazy. So you're just moving water from one area and then putting it into the ground at another point. So really simple stuff, of rehandling water that you should only touch once, but because of all that leaking infrastructure, you're having to deal with it multiple times before it actually gets out of the pit volume.
Yes, I support Phil. 100%. But you know what? I'll even take it a step earlier. The good news is a lot of companies, a lot of operations are seeing the value of surface water management. They'll get a consultant come in, put together a fantastic surface water management plan, a super report, and then not actually implement it or delay implementing it, or budget gets deferred. Why? Because it's not, as Travis said, it's not an immediate risk. It's not an immediate problem until it's a problem. And then it's like, oh, well, we had this plan, but the budget was cut. We didn't actually have time to do it because it wasn't immediate production need. But as I say, the good news is more, when I started my career, we didn't even talk about these things. Now, at least we all recognize the importance, and we're putting it out there, but then now it's a matter of following through, implementing it. And Phil, as you say, maintaining it.
Good discussion, guys. You hit all, I think we hit all the key points.
Yes, and we do have live questions that are starting to come in. All right, so we have a question that came in, which is related to another. So I'll just show both real quickly so we can talk generally and then also address the specific question. So the topic would be on how mines should balance investment between depressurization systems and monitoring systems. And then our live question from Clarence on the same topic is, how do you handle a project that's budget constrained in terms of not being able to afford both dewatering and VWPs at the same time? So we can talk specifically to the dewatering and VWPs, or generally to dewatering, depressurization versus monitoring tools and instrumentation. So I will open this up for a volunteer. I see Travis, you have your hand up to start. Please go ahead.
Yeah, thanks, Joel, and good questions. Look, I don't think balance is maybe the correct term. It's more what do you prioritize and what do you do when. So if you look at the full sort of mining cycle, from greenfields to when you actually have an operating mine, you're drilling hundreds, if not thousands, of holes. All right, and the biggest cost in a VWP installation is the hole itself. So if you've got 90% of the cost already covered, all it requires is a bit of teamwork, a bit of collaboration with the geotechs, with the geos, with whoever else is drilling holes, and then you just got to get funding for the instrumentation. So that's sort of the cheat code for that is to make sure that you piggyback off other disciplines, other departments, and that's how you get your VWP network in place. And I mean, every big large open pit within their geotech domains will have a hole, at least one. So, as a rule of thumb, that hole that gets drilled should be instrumented with VWPs. When it comes to the depressurization and dewatering sort of, combined, is, do the numbers. There's, Geoff and I have had discussions many times about trying to find a project where it was not feasible to dewater or depressurize in advance, and very, very few examples. Off the top of my head, I actually can't think of one. So do the numbers, and the other advice I would give is spend the money early. So geotech and hydro are the same. It's always going to cost you money. You're going to have to spend money on the drilling, on the instrumentation, on radars and pumps and pipes and everything else. The sooner you spend that money, the cheaper it is, and the earlier you reap the benefits. And then you can go into the next phase, which is then optimization. But I'd be very, very cautious of implementing a dewatering or a depressurization program if you don't have monitoring in place, because then you don't know how effective or ineffective your program is, and you might be, spending. You're definitely going to be spending more money in the wrong place, potentially by doing that.
Yeah, exactly, Travis. I mean, that justification of that spend is with the instrumentation and focusing the instrumentation on the parts that matter. Geoff showed that slide. The monitoring needs to be in the critical slip surface area, and I think the fortunate thing is that most of those are quite shallow. So using a blast hole rig to put VWPs in is a cheap way to fill in the gaps, and it puts the instruments in the area of interest. And I suppose the other thing is, end of the day, we need to justify why we spent $100,000 or $1 million on a depressurization plan, and just using the flow from depressurization holes is a really poor way of demonstrating that the money was well spent. I mean, dry holes can yield significant depressurization because the water goes into the fractured ground that Geoff was talking about earlier. The only way to really give that meaningful measure of success is VWP. So flow out of a depressurization hole is not going to tell you the full story. And ultimately, we need to explain to management that the program was successful, or we need to spend more money because we didn't meet the depressurization targets, and we still have a poor pressure issue that needs to be managed.
Yeah, I mean, having been involved with many failures over the years, I would make kind of three key points, I guess. If you get a failure, simplistically, there's three things you can do. There's unload the top of the slope, big dollars. You can buttress the bottom of the slope, big dollars, sterilizes all. Or you can depressurize. Depressurization is typically a fraction of the cost of slope management compared to the other mitigation options. Secondly, as geotechs, we don't do a very good job as a geotechnical community of telling management what we're spending our money on. We're always got our hand out looking for money for instruments, for holes, whatever it is, but we never tell our management what that money's going to buy us. And that's, I think, a big oversight, and it means the management will not understand why they're spending the money and therefore be reluctant to release the money. And the third thing is just in general dewatering, right? General dewatering is expensive, but so is wet blast holes. Years ago, I did this study, and I've repeated it many times. The cost differential, if you're using ANFO versus emulsion, the cost differential between a dry and wet blast hole is a couple of $100 for one hole. You multiply that by many blast patterns, and you've made your money lots of times over. But we never tell that to our management. And, you know, how many projects have I been involved with or how many times have I sat here and got a phone call and said, oh God, we can't advance our pit floor. We can't sink our pit floor because we can't load blast holes because there's too much water. We don't point out the value that we're giving to the mining operation near enough. So I think that's something we need to be more aware of. It's something that I try and tell people to do. Okay, go ask for $1 million, but go and tell your manager what it's going to buy him.
All right. Thank you very much for that great question, Clarence. And any final comments from the panel before we move on to another? Okay, so I'm going to direct this one to Geoff, considering his emphasis on surface water, excavation damage zone, other topics that he discussed in the talk. And I did want to make a quick note as well for our participants that the webinar was recorded. Someone requested the presentation, but you will be able to view the presentation again on our YouTube page. So yes, but Geoff, I'll send this to you to start and then open to the panel. So Marco's asking, beyond superficial erosion and raveling, do you see any issues with ditching water perpendicular across benches so that water drains over bench faces down to the bottom sump? If you'd like to comment on that.
I've just submitted a report today to a large mine in Canada where water was running down ramps straight into an unstable area. So what I said to them to do was, okay, you're never going to be able to pump that water from the slopes. So identify an area of strong rock and put water bars or cross drains across the ramp. And rather than letting the water go into the weak material that's already failed or into tension cracks, bring that water down the slope in an area of strong rock. So I think that's probably, it's not only an issue, it can be good practice, provided you understand the strength of the rock that you're bringing the water down. One of the fundamental issue with surface water management always starts with mine planning. And most pits have disused ramps, what I would call legacy ramps. So you have a ramp which gets consumed by a pushback or change in the mine plan. So the ramp then leads to nowhere. Often you can't access that ramp. So what happens? Water will flow down that ramp, drop out the end of it, and whatever's at the end of that ramp will have concentrated water flowing into it. Again, you look around, and particularly in wet climates, many instabilities are related to old ramps where water's run down them and got into the weaker or already failed material. So to answer your question is no, there's no issues provided you understand what you're doing and provided you make conscious and well thought out decisions.
Thanks, Geoff. Any other panelists like to chime in on Marco's question?
Actually, Marc Ruest, one of the panelists, did a great job with that on the old Victor Diamond mine in Canada.
Which one? Are you talking about Phil or are you talking about me? We're both De Beers people.
You. Oh, no, you. You remember that? Yeah. Remember that strong kimberlite in the North Wall? Can't remember that you brought the water. I've got many photos of that water coming down that ramp to get it away from the less stable areas.
Okay, you might be giving credit to the wrong person. It's probably Phil.
Maybe it was Phil.
All right, I'll pull up a next question. We have about 10 minutes left in the webinar, so we should be able to get through a few more questions. Marc, while we have you, I'm going to ask you if you would be willing to start off this question here. So what is the most common misconception that you see geotechnical teams make regarding pore pressure in open pit slopes?
I'm glad that came up. I was kind of worried, due to time constraints, that it would fall off the map. But if you look at this presentation that Geoff did, I mean, it's exactly the situation. It's exactly the situation that we're dealing with in all of our pits, and that is, the difficulties we have that are associated with water are way more complicated than what we put in our design, in our models. How often do you see any geotechnical design report that has any discussion on the issues that Geoff brought up today? And those are the things that drive pit stability. And so, that to me is the biggest misconception is how we talk about it at the design phase and then the reality of what happens when we're actually mining the pits. What I would really like to see is that now our geotechnical design reports incorporate those discussions, particularly when it's a pushback and we have the experience at the site and we know the problems that we have at the site that are water related. Put that on paper, keep those records in place, and put the measures in place so that when we mine that pushback, that we're dealing with it properly. So that's one aspect. And the other aspect is, how do you treat these pore pressures in slope design? And, we've had these debates. Do we put the pore pressures just in the rock? Do we put it in the major structures? Do we put it only in the joints? I thought that was resolved with the LOP project. It isn't, because I'm still seeing consultants do different things. And so again, the other misconception is, how do we represent those pore pressures in our design models?
Which Geoff had said would possibly be a topic of discussion, as he showed those 5 options. Travis, you have your hand up? And then Simon?
Yeah, Mark's spot on. And I mean, the number of times I've seen a slope design where, the assumptions for water is that the slopes in the pit are going to be dry. And I did a bit of digging on the reason why, and it's all about economics, right? So the open pit in any mine is going to be the largest piece of infrastructure at any mine, right? It's where every rock that goes to the mill or goes to a waste rock dump comes from. But it gets the least attention, but it's also the biggest cost driver. So, things like your stripping ratio. So the dry slopes make the economics work because you can mine steeper, which means you can mine cheaper and you reduce your costs, and your project becomes more feasible. Where the wheels fall off is they assume dry conditions, whether they're dry or not, and they never implement the controls to achieve those design assumptions. So there's nothing wrong with assuming that the slopes will be dewatered or depressurized if you actually do the work to implement the controls that you need, like a dewatering program, depressurization program, VWPs, and the works. So one of the misconceptions I would say is that the assumption is that the pit will be dry, and it very, very seldom is.
Thanks, Travis. Simon, do you have something you'd like to add?
It's it's an observation in that about 30 years ago when I started working with Geoff in northern Chile on dewatering, depressurization, most of the work was kind of directed by geotechnical engineers. But over the last 20 years or so, I've seen that work kind of be outsourced by the geotechnical group to hydrogeologists. And often hydrogeologists that have gone to university, and like I did, and studied hydrogeology in the classical sense, where they don't know anything about how a pit face works. And this presentation that Geoff gave now, and the way water flows, particularly in the shallow zones and the fracture zones, and how the hydrogeology actually flows through the system, how the water flows through the system. And so there's this misunderstanding between hydrogeology and geotech on what you're monitoring and how you're describing it and how you're taking it from hydro models to geotech models, producing these ball pressure gradients that really don't, as Travis said, or I think it was Phil said, you're hoping for a dry slope. And you put that in your model and in your slope stable, but then you find it's not dry and you don't know why. So it brings up my question. I think it's one of your prepared questions was, when do you start to see that your conceptual model is wrong and you have to reinterpret to re-understand the hydrogeology? And I think part of it comes from this outsourcing to people that are not miners.
Simon, I think what goes hand in hand with that is also a wrong expectation that people read corporate standards that talk about you need to have a hydro model to put into the stability model, but that hydro model doesn't necessarily need to be a numerical model. So then that drives these big, complicated pore pressure grid models that don't have enough data to calibrate them. And you're off down this rabbit hole with this model that's precisely wrong. Instead of spending the time to look at the data, and like Mark was talking about, if you've done a pushback before, you've got some experience on actual dissipation of pore pressures and using that data to better understand your conceptual hydro model, and then using that to constrain or bookend the credible range of best case, worst case depressurization scenarios, and put those into your stability model and use that to drive decision making rather than relying on these cool looking numerical models with nice colors on them, but are really poorly constrained.
I agree. And often it takes you 6 months to get the wrong answer.
All right, we have just a few minutes left, so I think I'll pull up just one more question from our live audience. I did want to note that our panelist extraordinaire, Travis White, is typing some answers to questions since we have more than we can answer verbally today. So if you go into your Q&A window and you go to answered, you can see typed responses that are in there, and I'll leave the webinar open for maybe 5 minutes or so afterwards so that you can go in and read that. And I will pull up one final question, which hopefully won't be, let's see, from our live group. So talking a little bit about underground advancement. I know many mines are advancing underground. Does the panel have any guidelines, thoughts, tips on how far in advance should dewatering be implemented ahead of underground advancement? So Geoff is our featured speaker today. Would you like to start this one?
Yeah, I think one of the issues that you face with an underground mine is that as we've seen for the open pit examples, there's typically more water close to the surface, and as you get deeper, so yeah, you might get some fractures, but the overall porosity is lower. So many underground mines, by their nature, have to do their development, their declines, their shafts before they've really got their hands around the dewatering. So I think when I look at an underground mine, and if you guys do the GC underground course, which is happening, I think, right now, or just about to happen, you'll see that,
September.
yeah, okay. So you'll see that, you know, I categorize underground development differently from underground production. So, you know, many times we have to do grouting, advanced dewatering, freezing of shafts, declines, so on and so on. Whereas when we get down to the main ore body, dewatering can be a lot easier. So it's a question that doesn't really, you know, the answer to the question is, of course, it depends on the situation. But I think the main thing to consider is the timing of the mine and the timing of the development, and could you reasonably dewater that in the time you have. So there's a good example which I've actually thrown into the underground watering course when we the underground dewatering section. When we did the Lachine mine in Ireland, when we put the decline back in there back in the 1990s, I think it was. Very permeable karstic limestone, and the ore body was 300 meters deep, but we had shales in the footwall. So we drove the decline down shales in the footwall, so the decline popped out into the ore body at 180 meters depth. It took us 2 years to do the decline, and the goal was within that 2 years, we'd done pumping from the surface to get the water level down to the level of the workings while we were doing the decline. So as we were doing the decline through shales, we were dewatering the permeable limestone. Did it work? The answer is yes, but of course it didn't work perfectly, and so we had to do a lot of initial dewatering from underground. But essentially, that was the concept. 2 years to dewater a really permeable limestone while we were drilling the decline. So by the time the decline got into the permeable limestone, it was essentially there was enough pressure off the limestone that we could mine it. So probably the answer to your question is any time between 6 months in a fairly tight formation to 2 years in a permeable limestone.
Not bad. Any additional comments from the panel? All right, Geoff, you did a good job. So there are additional written responses. Phil, thank you for joining in, answering some of the questions that were left in our Q&A. So I will leave that open. I'll leave the webinar open for you to go in and read those questions. I am going to close out with just a thank you, first of all, to our panelists and our participants. It's always a very popular topic and a great discussion when we're talking about water and mining. We will definitely have another webinar focused on water. We do vary our topics based on all of our courses that you see here listed. The one that Geoff was talking about, which is our newest course currently in development, is Geotechnical Fundamentals for Underground Mining, which we are working with industry experts from around the world to develop that content, and it will be launching in September of this year. So we're very excited about that. And then you can go to our website, which is www.mining.arizona.edu/GCE, and you can learn more about our courses, or you can scan this little QR code here. And then specifically, if you're really interested in water, we have a course all about that, and it features some of our panelists here today, Geoff, Phil, Travis, and it is 30 hours approximately, all online, self-paced, and currently open for registration. You have access for a whole year, so I will leave this on the screen. So if anyone wants to scan that and join that course, it features Geoff Beale, maybe 75%. Really good teachings and a lot of good knowledge transfer from industry that's very practical and applied. So yeah, highly recommend. And thank you again to our panel today. We hope to see you again in another webinar. We really appreciate your time, and thank you to our participants. I'm going to go ahead and say goodbye, but I will leave the webinar open so you can go in and read the answers to those questions. So thank you, Geoff, Simon, Phil, Travis, and Mark. And everyone have
Thanks, everybody. Thanks
Cheers,
to
everyone.
my
Thank you.
thanks to my
Cheers.
co-panel for some good discussions and some good questions.
Thanks, Geoff and everyone.
Cheers, guys.
Okay, see ya. Thanks. Bye.